Welcome to view the video lesson on Light, Reflection and Refraction Part 2. This video lesson deals mainly with refraction of light, laws of refraction, refractive index, refraction by spherical lenses, and also ray diagrams to understand the refraction by spherical lenses, magnification, mirror formula, and the power of lens. Hope you like this lesson. If you like it, please click on the like button and also subscribe for my channel Learn Science with Usha Raghupati. Dear children, light seems to travel along a straight line path. What happens to the light when it travels from one transparent medium to another? Does it take the straight line path or will it change its direction? Let's recall some of the day-to-day experiences. You might have observed the bottom of a swimming pool or a tank or a pond filled with water appear to be raised. Now, another example is you might have observed if you view through a thick glass slab kept on a printed matter, the letter appear to be raised. Why does this happen? Another example is if you observe a pencil partly immersed in a glass tumbler containing water, the pencil appears to be displaced at the interface of water and air. Also, a lemon kept in a glass tumbler containing water, if you view it from outside, the lemon looks bigger than its actual size. Let's understand all these things. Let's take the example of a pencil, which is partly immersed in water and which appears to be displaced. The light that reaches you from the part of the pencil below the water seems to come from a different direction compared to the light that reaches you from the part above the water. That's why the pencil looks to be displaced at the interface of air and water. For similar reasons, the letter appears to be raised when viewed through the thick glass slab. Now, all these examples or observations, we understand that the light does not appear to travel in the same direction. When the light travels obliquely from one media to another media, there's a change in the propagation of the light. This phenomena is called as refraction. So all these examples are due to the refraction of light. Let's understand more about refraction of light. Refraction is the phenomenon of change in the path of light as it travels from one medium to another when the ray of light is incident obliquely. It can also be defined as the phenomenon of change in speed of light from one medium to another. Observe the picture. Now, refraction occurs due to two laws. What are the laws of refraction? The first law says that the incident ray, the normal to the refracting surface at the point of incidence, and the refracted ray all lie in the same plane. The second law states that for a given pair of media and for light of a given wavelength, the ratio of the sine of the angle of incidence to the sine of angle of refraction is a constant. This is an important law and it is called as the Snell's law. Here, mu is equal to sine I by sine R, where the constant mu is called refractive index of the medium I is the angle of incidence and R is the angle of refraction. Let's understand more about the refractive index. A ray of light that travels obliquely from one transparent medium to another will change its direction in the second medium, isn't it? The extent of change in direction that takes place in a given pair of media is expressed in terms of the refractive index. The refractive index can be linked to an important physical quantity, the relative speed of propagation of light in different media. Light travels fastest in vacuum with the highest speed of 3 into 10 raised to 8 meter per second. In air, the speed of light is marginally less when compared to vacuum. Consider a ray of light traveling from one medium to medium 2, that is medium 1 to medium 2, as shown in the diagram. Let V1 be the speed of light in medium 1 and V2 be the speed of light in medium 2. The refractive index of medium 2 with respect to medium 1 will be given by the ratio of the speed of light in medium 1 and the ratio of the speed of light in medium 2. That is the symbol N21, which represents the refractive index of medium 2 is equal to V1 by V2. V1 is speed of light in medium 1 by speed of light in medium 2, V2. By the same argument, the refractive index of medium 1 with respect to medium 2, that is N12 is equal to V2 by V1. Now, let's understand about absolute refractive index. If the medium 1 is air or vacuum, then the refractive index of medium 2 can be called as absolute refractive index of the medium. It is represented as N2. Now, if C is the speed of light in air and V is the speed of light in the medium, then the refractive index of the medium Nm is equal to speed of light in air by speed of light in the medium, that is C by V. Here you can see the refractive index of different medias like air, ice, alcohol, kerosene, quartz, turpentine, benzene, crown glass, and different many other. Diamond has got the maximum refractive index. So these values can be used for you during when you do the problems. Let's understand the refraction of light by convex lens. A convex lens forms an image by refracting light rays, and the light rays reflected from an object are refracted when they enter the lens and again when they leave the lens. They meet to form an image. Observe the pictures. Now, what are the rules for converging lenses? Refraction rules. And any incident ray traveling parallel to the principal axis of the converging lens will refract through the lens and travel through the focal point on the opposite side of the lens. Any incident ray traveling through the focal point on the way to the lens will refract through the lens and travel parallel to the principal axis. An incident ray, third rule says that an incident ray that passes through the center of the lens will in effect continue in the same direction that it had when it entered the lens. So these are the three rules for the refraction by convex lens. Now let's understand the refraction rules for a diverging lens, that is concave lens. The first rule says that any incident ray traveling parallel to the principal axis of a diverging lens will refract through the lens and travel in line with the focal point. That is, in a direction such that its extension will pass through the focal point. Observe the picture, first picture. The second picture shows the second rule. Any incident ray traveling towards the focal point on the way to the lens will refract through the lens and travel parallel to the principal axis. And the third rule says an incident ray that passes through the center of the lens will, in effect, continue in the same direction that it had when it entered the lens. So these are the three rules for concave lenses. Let's now understand the ray diagrams for the image formation by a convex lens or converging lens for various positions of the object. Before going into detail, we all know that for a convex lens, there are two optical centers, C1 and C2 on either side, and also two focal points, F1 and F2 on either side of the lens. Now let's come to the first position of the object, which is at infinity, and the image is formed at the focal point F2 on the other side of the lens, and the image is point-sized, highly diminished, and real and inverted. The second diagram shows the object beyond 2f1. The image is formed between f2 and 2f2, and the image is diminished, real and inverted. The third one shows that the object is at 2f1 and the image is at 2f2, which is of the same size and which is again real and inverted. The fourth picture shows that the object is between f1 and 2f1 and the image is formed beyond 2f2. The image is real and inverted and magnified. And the next one is, that is the fifth diagram shows the object is at f1 and the image is formed at infinity and the image is highly uh, enlarged, and it is real and inverted. And the last picture shows that the object is between F1 and the optical center and the image is formed on the same side of the lens and it's also enlarged, but it is virtual and erect. Now let's understand the ray diagrams for the image formation by a concave lens or a converging lens. The first diagram shows that the object is at infinity. Image is formed at the focus 1 and it's virtual, erect and point-sized image. The second diagram shows that the object is at any point between infinity and the optical center and the image is formed between F1 and O. And the image is virtual, erect and diminished. Just like we have lens formula for spherical mirrors, we also have lens formula for spherical lenses. This formula gives the relationship between the image distance, the object distance, and the focal length of the spherical lens. So the formula is as follows: 1 by V minus 1 by U is equal to 1 by F, where V is the image distance, U is the object distance, and F is the focal length. We should all remember that according to sign convention, the focal length of the convex lens is positive and the focal length of concave lens is negative. Now, magnification of a lens is the ratio of the height of the image by the height of the object. That is, M is equal to H dash by H, where M is the magnification and H dash is the height of the image and H is the height of the object. Magnification produced by a lens can also be related to object distance and image distance as follows. M is equal to V by U. That is, it is the ratio of the distance of the image by distance of the object. Now, power of lens. What is power of lens? The degree of convergence or divergence of light rays achieved by a lens is expressed in terms of its power. The power of a lens is defined as the reciprocal of its focal length. So, there is a relationship between the power of the lens and the focal length, and P, the power of lens, is equal to 1 by F. The SI unit of power of a lens is diopter, and it is denoted by the letter capital D. 1 diopter is the power of a lens whose focal length is 1 meter. That is 1 D is equal to 1 M minus 1. Hope you like this lesson. If you like it, please click on the like button and also subscribe for my lesson, my channel, Learn Science with Usha Raghupati.